Okay, so we'll pick up with question number 5, which is an absolute value problem. And with the absolute value problem, we know that the only way to show a derivative is with limits. So that's one of the things that I keep stressing with the absolute value problems. But knowing the knowledge of our past and where it moved up, down, left, right, or reflected automatically can tell us where our cusp is. So that's important because you can get there a little quicker to know what your focus should be. So this problem is not in the correct format. Why? Yeah, that's right. The 3's in the front. So sometimes knowing that can help you to see that up, down, left, right, reflect type look. This problem does what? Reflects, okay. You said right. 5. Why? Because it always does the opposite inside the absolute value bars, because you're supposed to set it equal to 0 and solve. And up 3. So now that we know that, we know where the relative... Is it going to be a max or a min? But it's technically a cusp, right? But it is a max or a min thought, because that's what we studied back in Math 3. That when it reflects, it makes a max. But we're going to call it a cusp because of the way it doesn't have a denominator, but the derivative does. So, in looking at the derivative, we're looking at the limit of x as it approaches. What value is my derivative most important about? Right, that number that makes it go to right or to the left. So in this case it would be 5. And we'll look at it from the positive side and the negative side. Now, as we work out these limits, we know that it's the formula minus the value at that place for y over x minus that value of x. It's f of c minus, f of x minus f of c. Let me write that down. F of x minus f of c over x minus c is your slope formula. So we put the function minus the value at that x. So our function, that looks like a parentheses, minus what? When you plug in 5, what do you get? 3? Is that what you said? Alrighty. So you always get the up number, which is why it's so important to learn those up, down, left, right, because it gives you a lot of stuff. And this will be x minus 5 because our value that we're focusing our limit on is 5. So the 3's drop out. So we end up with a denominator, even though the original problem didn't have a denominator, and that's what causes this to be a cusp. Now, when I take the absolute value bars off and want to write my formula, there's already a negative in front of it, and when you do it from the left, you put a negative on it. Does that make sense? And when you do it from the right, you don't put the extra negative on it. So the limit on the left comes out to be positive 1, and the limit on the right comes out to be negative 1. Now let's see if that makes sense. We did say this is a max, right? So this side has positive slope, and this side has negative slope. So the left side has positive and the right side has negative. Makes sense, doesn't it? That this relative max, or what we call a cusp, really does fit what we said it does. So now, how would you show this with a sign chart, because you might be asked to write a sign chart for an absolute value problem where you can't plug numbers in. That wouldn't work. This sign chart would not have the same well, I could plug numbers in. It just wouldn't make sense to plug numbers in because the derivative is a constant. Does that make sense? So when we look at our interval chart, we're looking at negative infinity up to 5 and 5 to positive infinity. So when we say f prime of x equals, and we plug a value in, it doesn't matter what value we say we're doing. It's a constant answer. So we're not going to be evaluating it, but we can pick a number, and that's not the problem. The problem is it'll have the same answer no matter what we pick on the left side or the right side. So if I say the derivative of 4, then it's going to be positive 1. And if I say the derivative of 6, that's going to be negative 1, because everything to the left of 5 is 1. And everything to the right of 5 is negative 1 because it's a constant slope. So then when we talk about our plus or minus or our increasing, decreasing, and hopefully the heat will turn off in a few minutes. I took it out. The thermostat has to get warm enough to actually take you. So hopefully it'll do that in a minute. So now we can see that it went up and it went down, and that makes it a max, right? But we call this a cusp. At x equals 5, there's a cusp because it's a very pointy relative max. So we call them cusp because it has a derivative with a denominator and the original one does not. All right, so just a little different work here to show the, yeah. All right, now the last thing I want to look at is I have a problem that's a radical problem. I chose this one because I wouldn't want to have to do the derivative of this by hand. It would be nasty. So if you don't have your 89 out, you might want to get it out. Bless you again. Wished I could read my handwriting. Utility. Utility? Did I spell it right? Okay. I didn't cross one of the T's on my paper, and I thought, that don't look right. Alright, so this problem is going to pull everything that we've discussed back together, but using our calculator to do even more of it than before. We're going to use the symbolic differentiation utility to differentiate it because it's a problem that would be a very involved problem, would need a lot of algebra to straighten it up. We're going to sketch the original problem, and we're going to sketch the derivative from what our sign chart tells us. And we're going to find the critical numbers from that derivative and make that chart to see what do those critical numbers tell us. All right.
I thought that derivative, I thought it was an exclamation point.
No, that's a prime mark. But I can see why you'd think that looks like an exclamation point. Yes, we're excited. We get to use our calculators and don't have to do the derivative of this problem by hand. Since it's a product rational problem, that's a pretty good reason not to. Because a product with a rational usually ends up having denominators that need rationalizing and get a common denominator, and the calculator doesn't even do it all for us either, but that's okay because we're really just focusing on the critical numbers. All right. So on your 89, you're going to type in this problem, but remember you got to type times marks because your calculator's not smart enough to know sometimes what times means. Sometimes it'll do it and sometimes it won't. Depends on what you're putting together. And you're going to do the derivative of this value, of this function, so that we can, and they limited this particular problem for a reason. And I think you'll see why they limited it for a reason here.
Yeah, this is ugly.
Yeah. All right. Now, what is your utility giving you?
2 square roots of 9 minus x squared.
Uh-huh.
Minus 2x squared over the square root of 9 minus x squared.
All right, so does everybody see that before, when we worked answers like this, we got a common denominator and put it all together? And that would be, something we would need to do. Even if we were doing this problem by hand, we'd still have to probably, do a lot of that. But since we're doing more of this one on the calculator, we're not going to take the time to get the common denominator. But we know the common denominator would be this, right? Well, that causes a problem. Because if that's in the denominator, that means there's going to be something going on in my problem. For one thing, the original problem doesn't have a denominator, but your derivative does. So I may have some cusp going on, or something else going on in this question. So if I look at just this denominator part, 9 minus x squared equal to 0. I took the square root off of it because it's really what's inside of that's going to be 0. Taking the square root of 0 would be 0. So the square root, you could just square that off and say it's gone. And this ends up being 3 minus x and 3 plus x if you factor that with food line without cleaning it up. You don't really have to clean that one up since it's that simple. And so 3 and negative 3 are going to be a problem in this graph. Can everybody see that? Now, I could have turned it around and took a negative out, and it'd still be the same two numbers. So sometimes it's just easier to leave your food line the way it is and not turn it around. Now, the next thing you need to do is take the entire problem itself, copy that answer. Now, listen to what I'm saying first. So that we can solve it equal to 0, you want to go get the solve word first. And then you want to copy this answer from the derivative and into your solve answer so that you can put equal to 0 comma x. Because if I'm not going to get a common denominator by hand so I can solve it by hand, then I need to use the calculator to solve the entire thing equal to 0. And it should give you the exact answer to the question so that you know what x can't be equal to on the top. Because that's what it's going to do. It's not going to tell me the vertical asymptotes or anything that's an issue with the bottom, which could cause cusp or anything like that. But it will tell me what makes the top equal to 0 with me not having to get a common denominator to do that. Does that make sense? So what are y'all getting? Everybody agree? Okay. So x is equal to plus or minus 3 square roots of 2 over 2 is the values that came from the just solving the derivative equal to 0, which has to be maxes, mins, or inflection points. So in that particular case, making my sign chart will help me to determine what all these things are causing. Okay? Now, to make my sign chart, though, I kind of need to know the decimal for that because I got to know where to put it. I don't know if it goes before 3, after 3, between the 3s. I have no idea. Which I'm hoping that goes between the 3s. Because that's what my domain was. So it's definitely between there. So we definitely have a situation where they gave us this domain up here is -3 to 3. They cut it off with that and said there's nothing outside of that. So I was hoping that these values were between there, because if they weren't, I'd have a problem making a chart. All right. So now that we know they're definitely between there, then our interval is going to be from -3 to the -3 square roots of 2 over 2, and then the -3 square roots of 2 over 2 to the +3 square roots of 2 over 2, and then the +3 square roots of 2 over 2 to the 3. And these are all open intervals because it's dealing with a derivative. Now, another reason why you needed that decimal is because that will help you to choose a value in here. Now, what was that decimal again, y'all? Because I didn't hear y'all good. 2.12. Okay, that's my decimal. All right. So when I do my derivative and I'm evaluating it, now I'm just going to help you get this set up, and then I'm going to let y'all finish out the table. I've got to pick numbers that work. So if this is -2.12, then -2.5 would be in that first one. Would everybody agree with that? I can't pick a whole number in there. I got to pick a decimal. So -2.5 would be the best decimal to choose. All right. Now between here, I could pick 0. I could pick a whole number. Or I could pick -1 or +1, because it's from -2.12 to +2.12. So I like picking 0. And then over here, I can pick +2.5. Because if I pick -2.5 in this one, then it would make sense to choose the same value in the positive range. All right, so I want y'all to evaluate that, and then I want you to fill in your positives and negatives and your increasing and decreasing, and see if you can determine what you think this problem does. You plug those into the derivative, yes. All right, so what you're doing is trying to see what is happening between 3 and -3. But 3 and -3 are where we found the values of the denominator of the derivative are undefined. Normally that means you have vertical asymptotes or cusp, but in this problem it doesn't mean that. So we might need to talk about what does 3 and negative 3 really do in this question, because that might be important to know. So what I'm going to suggest you do next is I would like you to put the original problem in y1 and your derivative equation in y2. And I want you to bold one of them, or you're going to have to watch to see which one graphs second one. Yeah, it works better in the other one to bold. And graph them both and draw a rough sketch on your paper so that we can discuss what the two graphs look like in terms of our table and what do those negative 3 and positive 3 really represent in this question. And I'm going to pause the video while y'all do that this time. All right, so when you did your table, was it decreasing, then increasing, then decreasing? All right. So we know that at positive and negative 3 square roots of 2, that we either have some cusp going on or some maxes or mins or something, because that came from the derivative, right? Well, we also have the fact that the denominator couldn't be 3 or negative 3 in the derivative. What does your calculator say on the table that negative 3 of the original problem is? 0? Does everybody agree with that? That when you plot negative 3, it's at 0. When you plot positive 3, it's at 0. But did your graph go back down and touch the x-axis? Yeah, it's got a little problem here. It's having trouble drawing that back down there, but you're telling me the table says 0 for negative 3 and positive 3. And that's because it limited your window to in between these two lines, and your derivative came out with 3 and negative 3 can't be in the denominator. So it's having trouble drawing back to that because it's so straight up and down. And I'll explain why here in just a second. Can you tell me what the value for y for those two decimals were? The 3 square roots of 2 over 2 and the negative 3 square roots of 2 over 2? It was 2.12, but what's the y value that goes with that off your table? Now, you might have to do value on your graph to get that, because we need the y value to go. The original. All right, so when I go over negative or positive, to get, all right, for the positive. So if I go over 3 square roots of 2 over 2, which is 2.1 something, you're telling me I have to go up 9. And the other one's down 9? I figured it'd be symmetrical. Okay, and it goes through the origin. Okay, now we know that this kind of makes sense because the graph is increasing and decreasing at different places, and it's supposed to be increasing all the way from this first point to that last point. But there's an inflection point in there that we don't have because you can only get it from the second derivative. And then we know that it says it's decreasing after that. So our calculator started to make it come down like this. Oh, little problem. It couldn't draw it to there because it's so vertical. See how flat and vertical that last piece looks? Our calculator's lying to us by not connecting it up, even though the table's given us a value at 3 and negative 3. It's having trouble doing that because it's so vertical. And these aren't really vertical asymptotes, but I drew those in because our derivative came up with those numbers saying there was a vertical asymptotes in this problem. There really aren't any vertical asymptotes in the original problem, but it looks like that might be why it's having trouble drawing to that point, is because it's so vertical, straight up and down. And then when you did your derivative, I'm sure it had some kind of similar issue. It looks like something like this. Parabola, right? Now, the derivative can't touch these 2 points. which is why it's further in. And it may have a little trouble drawing that down to the axis. And I probably don't have this side really good. Let me try that again. It's having trouble drawing it down to the axis also, because does yours touch the x-axis?
Mine goes all the way down.
Oh, well, then we need to draw it a little further. But where it's touching the x-axis is that negative 3 squared roots of 2 over 2. That's where it's supposed to be touching it.
Yeah.
And then you're saying it goes on further. Well, look what it's doing when it goes on further. It's still staying between those two lines. It's not crossing 3 and negative 3 yet either. And that's what those two fake vertical asymptote are for, because they're not really real, but they do help you to line it up because it came from the derivative. And it even still focuses on what we've been talking about. That one looks like a cubic that turned to a quadratic when I took the derivative. All right, so that's kind of where we're at. So back to what we're talking about in terms of labeling. So this point down here at the bottom looks like a min, and this point up here at the top looks like a max. And are they really pointy on your graph more so? No, still looks curved. Okay. And I was trying to think how to explain this. Okay. You know how we know every time we do an absolute value problem that the max or the min is going to be a cusp. And that sometimes when we do the problems with other problems, there's cusps because it's pointy. How I know these two aren't cusp is because they didn't come from the denominator. The cusp always come from the denominator because there wasn't one and then there is one. So in this problem, these are really relative mins and relative maxes. And that's why they look rounded. Technically, in this problem, the endpoints are the cusp because they came from the denominator. Think that through. They came from a denominator, right? So they would be the cusp. But because there's no graph on the other side of it, you can't see that. But they would be cusp. So up here, these two would be cusps. Is it PS or SP? I can't spell.
I mean, SP.
Thank you. Cusp. All right. Those two are cusp, but they're on the edge of the graph, so we don't see that pointiness because there's not another side to it. But they came from a derivative, which did not have a denominator in the original problem. That always causes a cusp. And then again, like I said, this one would be your relative min, and this would be your relative max because they look like maxes and mins because they came from the derivative being equal to 0 on the top. But this would have been a lot of work. It took 2 boards worth for me to show you all that math by hand. And that's why having the utility on the calculator can be helpful. All right. So that is the end of our notes. So I want to assign a few problems for you to do out of the book that relate to some of the problems that we're having here with the graphing utility. I also want to throw in a couple of more problems today that I didn't get to yesterday. See, because yesterday I said stop at 16, right? Okay. So I want you to do 18 and 20 because one of those is absolute value. And one of them is a denominator problem, so that would be good to try.
Page 176.
Still page 176. So we're going to do 18 and 20. And then we're going to skip over and look at 30 and 32. They're trig problems, and they tell you to do it from 0 to 2 pi and stay within the unit circle and not go outside the unit circle for other points. But you may find that you can't solve it by hand to get your max mins or anything because it depends on how bad the derivative looks. So if you have to solve it on the calculator, you can. And then I want you to do question 34 and 36. That's your symbolic differentiation problems. And then the last thing I want you to do is there are 3 problems that have been sketched in your book. It says that a function f has sketched in the figure, sketch the graph of the derivative. So that's like what we did on the worksheet that I need to take up today. So I want you to do 44 through 48 even, where you are taking the original problem and sketching a derivative graph to go with it. All right, let me start this video thing for Destiny.